PauseBuds is a device that allows users to control music on their smartphones from their headphones. By simply removing the headphones from one's ear, this tells the user's smartphones to pause. Put them back in, and the music starts again. For Project 1, we managed to get a working prototype that utilized a temperature sensor in combination with Arduino to send a message to the phone to pause. In Project 2, we focused on making a more portable solution that was more likely to fit in the cord of a pair of earbuds, while looking at even more sensors for detecting in-ear activity. Additionally, we further explored the possibility of utilizing frequency shift keying, or FSK, for communication between our device and the smartphone. To create a portable solution, we considered a few important points. First off, we felt using Arduino was just a little too cumbersome. It didn't exactly scream portability, so we looked into alternative microprocessors. Very quickly, we found that the ATtiny85 seemed a perfect solution. The Arduino Uno uses an ATmega 328, with quite the impressive array of I/O. For our project, however, this wide-range support was unnecessary, so we opted for the ATtiny85, a simple 8-pin microcontroller. This particular model is so popular, there is significant support for Arduino libraries, which meant that simple code transferred painlessly to the new chip. However, we had to dive a bit deeper to find out the underlying hardware support for interrupts, specifically which registers we had to set up and the speed differences between the two microcontrollers. Powering our device also had us asking the question, how can we make this small? Of course, the answer lay in batteries. We looked into the different technologies and voltage counts that the batteries carried, compared them with the voltage range supported by our microcontroller, relay, and sensor, and decided that, while they're not the perfect solutions, CR2032 batteries will do for the prototype. At 3 volts each, we need 2 of them in series to get a high enough voltage to power our parts. As long as the sensor had a reference voltage for the power supply, we can correct for any straying from 5 volts, as long as we stay within reasonable bounds. Our sensor this time around was the pulse sensor we got from the Kickstarter Pulse Sensor open source heart rate sensor. The sensor is good in theory, utilizing light in order to measure the change in opacity of the skin as the heart pushes and pulls your blood. However, in application, there were a few circumstances that made it very difficult to actually implement for our needs. As part of the hardware design, the pulse sensor will recalibrate itself every few seconds in order to stabilize around the sensitivity of the skin. For a very long time, we were confused by the general behavior of the sensor in our different situations, and it was not until we hooked up the sensor to an oscilloscope that we realized what was happening. Unfortunately, this spells certain doom for the sensor in use with our product, because calibrating to light and dark situations will render any smart sensing of the situations meaningless. Frequency shift keying is a proposed method of communication between the smartphone and our device. All computer data is represented by ones and zeros. This means if we want to send data as sound, all we would have to do is pick a frequency to be high and a frequency to be low, and they would become the new 1 and 0. This is obviously not as efficient as simply sending the ones and zeros, but across an audio line and with small enough messages, it's perfect. Android phones already have an implementation of communication with Arduino called Androino. Created almost exactly a year ago, this app provides a service for other apps to use the FSK modulation and demodulation of signals. During testing, we found that we could receive signals well enough, but could never figure out how to send signals. After much deliberation and debugging and attempting to learn the complications of Android, we decided to leave support for FSK out of our final design. Additionally, there was a mitigating issue with the ATtiny85 that caused the code to stop working and, as far as we can tell, the software and the hardware each work when isolated, but broke when trying to work together, although a proposed complete prototype still supports the hardware. For the second phase of our project, we attempted to reach out in all directions to try to bring together disparate designs and ubiquitous computing into one set of headphones, but numerous hurdles and complicated debugging forced us to stop short of our final goal. To put it all together, we would have had a self-contained, relatively small board that would sit in between a smartphone and the headphones that use an ATtiny85 as the brain instead of the much larger ATmega 328 found in the Arduino Uno, powered by a set of batteries that used a customizable heartbeat sensor to sense whether headphones were in or out of the ear, which use FSK to intelligently change the state of playing music. Hopefully, one day, we will see or make such a device.